In the first section of Chapter 6, we introduced you to the standard normal distribution. The fact that this is the standard normal distribution should remind us that there is only one standard normal distribution, and that is the distribution of z-scores, which have a mean of 0 and a standard deviation of 1. In Section 2, we're going to look at x values that are normally distributed, but those x values don't necessarily have to have a mean of 0 or a standard deviation of 1. In other words, we're going to open up to considering all sorts of variables that have values that are normally distributed. So mu does not have to equal 0. And sigma does not have to be 1. However, of course, we're going to still be looking at that shape, that bell-shaped curve for the x values. The key concept in this section is that we will be looking at normal distributions that are not standard. In other words, they are not z-scores, but rather x values. Again, the mean doesn't have to be 0, and the standard deviation does not need to be 1, although they could be. The key is that we can use a simple conversion formula that will allow us to convert x values into z-scores so that then we can use all of the techniques that we learned about in section 6.1. Here is that conversion formula. For any given x value that comes from a distribution that is normally distributed, we can calculate the corresponding z-score with this formula. Z is equal to the value of x minus the mean mu divided by the standard deviation sigma. When we're working with z-scores, recall that we tend to take those calculations out to 2 decimal places so that we can use the table. This one step, converting from x values to z-scores, is what's going to differentiate the types of problems in this section from the ones you saw in section 6.1. Here's a graphic of what's happening behind the scenes when we apply this formula. On the left, we have a normal distribution that is non-standard because we see that we are working with x values. X could be temperatures, heights, scores on a test, for instance, so they can represent a variety of different quantities. The mean is still at the center, but it doesn't necessarily have to have a value of 0. By using this conversion formula, we can change the x value into its corresponding z-score so that we end up with the standard normal distribution, which is a distribution of z-scores. Recall that the mean of z-scores is 0 and that the standard deviation is 1. It is the same distribution. You can think of this as converting between, let's say, inches and centimeters. You still have the same length regardless of which unit you choose to represent that length. And the same goes here with these x values. When these x values are converted to z-scores, it doesn't really change what it's measuring, it's just changing its unit. Let's talk about procedures for finding areas when we are working with non-standard normal distributions. As before, you sketch a normal curve, label the mean and any values that are given in the problem. Then you shade the region that represents the area of the probability that you're calculating. Then using the table A2, you're going to look at what the x value that's given to you in the problem would convert to as a z-score, and then you use the table to find the appropriate area. Let's work through an example to illustrate this. Here we have that the heights of men are normally distributed with a mean of 68.6 inches and a standard deviation of 2.8 inches. It's important here to note that we are told that these heights are normally distributed. We're asked to find the percentage of men who are taller than a shower head that measures 72 inches in height. Taller means that we're going to find values that are to the right of 72. Well, because this is a normal distribution, I'm going to go ahead and draw a normal curve. And the mean, we are told, is 68.6. And we're trying to find the percentage of men who are taller than 72 inches. Now, I don't know exactly where 72 falls other than it's to the right. So I'm just going to put that here. I should not have put that little bar on top, so I'm going to get rid of that. So just x equals 72. I'm going to shade the area to the right because we're looking at the percentage of men who are taller than 72. Now, I want to convert this distribution into the standard normal distribution. So to do this, I'm going to calculate z equals 72, which is my x, minus 68.6, which is the mean, and divide that by the standard deviation, which we are told is 2.8. And I find that that z-score is 1.21. That means that I can represent the normal distribution as looking for the area to the right of z equals 1.21. And again, remember, the standard normal distribution has a mean of 0. So the two shaded areas are identical. They represent the very same probability, the very same percentage. Now, using table A2, I can look at 1.21 as the z-score that I'm interested in. So here is 1.2. It'll let me highlight this. It's not letting me. I'll just circle it then. 1.2, and then I'll go to the 0.01 column. So it looks like the area to the left is 0.8869. So area to the left of z equals 1.21 is 0.8869. But I'm not interested in the area to the left. I'm interested in the area to the right. So using the complement rule, I'm going to take the area to the left and subtract it from 1 to find the area to the right. So again, the probability that x is greater than 72 is equal to the probability that z is greater than 1.21, which is 1 minus the area to the left, and that will give us 0.1131. Now the PowerPoint notes here have a slightly different number, and that is because they use the calculator, they use technology as opposed to the table, but these are close enough that you would be marked correct on your homework or on a test. This is really just a difference between what we get using the table versus what we would get using technology. If you do want to use your calculator to find this, you do have the option to use the normal CDF command on your calculator, which is under your distribution menu. Now, sometimes our problems ask us to go in the opposite direction. Instead of looking for the area under a normal curve, we're given that area under the curve, and then we're asked to work backwards to find out what x value is the cutoff value for that boundary. To do that, again, having a graph is very helpful because you can label the different values that are of interest, shade the area that's given, and then help inform what steps to take. A reminder that you should not confuse z-scores with areas. Z-scores represent x values that have become standardized, and then areas represent probabilities which are under the curve for a given region. Remember to look at the wording in the problem very carefully. Words like taller in our last example indicate area to the right. So depending on the problem and the wording, You just want to be very careful to make sure that you are shading the appropriate area so that your calculations are accurate. Make sure that you remember that when we're working with z-scores, a z-score of 0 is right in the middle of the normal curve. Positive z-scores fall to the right, negative z-scores fall to the left. And then again, if you make a calculation error, one of the ways to catch yourself is to remember that probabilities all have to be numbers between 0 and 1. If you're calculating a probability and you get an answer such as 1.59, that's not an accurate answer because probabilities have to be numbers between 0 and 1. So here's a little summary of how to work these problems, and I think the best thing to do is to jump to an example so that I can walk you through the steps. This formula here under bullet 3 is the conversion formula for going from a z-score to an x value. So we're kind of just hitting the reverse button. You might remember the z-score formula is x minus mu divided by sigma. Well, if we want to solve for x, if we want to isolate x, the first thing we would want to do is to clear that denominator. So if we multiply both sides by sigma, we get z times sigma equals x minus mu. One more step, we'll isolate x. We've got to get rid of that subtraction of mu on the right. So we would add mu to both sides. So we would get mu plus z times sigma is equal to x. Well, that's exactly the formula that's given here. So this is not necessarily a new formula. It is the z-score formula that has been manipulated so that x is isolated. All right, let's take a look at an example. When designing equipment, one common criterion is to use a design that accommodates at least 95% of the population. What is the height of a door that would allow 95% of adults to walk through the doorway without bending or hitting their heads? We're going to use a data set from your textbook in Appendix B, and that data set gives us that the heights of all adults are normally distributed with a mean of 66.2 inches and a standard deviation of 3.8 inches. How does the result compare to the door height of 80 inches required by the International Residential Code? So there's a lot of numbers here. Let's sort through them before we jump into the mechanics. So we have a mean of 66.2 inches. We have a standard deviation of 3.8 inches. And we're asked what percentage of people would fit comfortably underneath a door if they weren't to bend or hit their head. In other words, that they clear the height of the door. So in other words, we want 95% of people to be able to walk through pretty well, and then the tallest 5% are out of luck. So here is the diagram for what we're looking for. Note that we have a normal distribution. We have labeled the mean height of 66.2 inches. And this shaded area represents the 95% of people who would fit comfortably under the door without bending or hitting their head. So over here we have tall people, right? The tallest 5% of people. And those are going to have problems walking underneath the door. Now, we need to find what the height is that will determine this boundary right here. What x value separates the lower 95% from the upper 5%? That is the question. Now, this is your normal distribution, and below it is your standard normal distribution. So non-standard because those are x values, and then your standard because those are z-scores. Using table A2, we find that The z-score that has an area to the left equal to 0.95 is closest to 1.645. So if this area to the left is 0.95, using table A2, we find that that z-score is 1.645. We can use that z-score now to find the corresponding x value. So I'm going to skip down to that chart here for just a moment. We're going to be looking in the body of the table, and we see that 0.95 as an area to the left falls squarely between these two values. And that corresponding z-score is 1.6 and then either 4 or 5, right? Kind of in the middle. That's where we get the 1.645 from. Now that we have the z-score, we can work backwards to find what the corresponding x value needs to be. Here's our z-score formula. Here's the z-score that we found, and we're solving for x. Excuse me. So we find that people who are 72.451 inches in height or shorter will be able to walk through the door with no problem. And the tallest 5% of people are taller than 72.451 inches. That means that if the building code is that door heights have to be at least 80 inches, then those doors will safely meet the requirement that at least 95% of people will be able to walk underneath the door with no problem. Basically, any number less than 80 for our answer would have made it okay.